The James Webb Space Telescope has done it again. It has discovered a galaxy so far away that its light has taken over 13 billion years to reach us. But the problem is, this galaxy should not exist. It appeared when the universe was less than 300 million years old, and yet it contains elements that, according to physics, should take at least 1 billion years to form. And if that is true, then it may mean we have misunderstood how the universe began from the very beginning. And if you find yourself drawn to questions like these, you can subscribe to the channel. It's a small action, but it helps this video reach more curious minds like yours. Because to understand what is really happening, we have to go back to the beginning and look at the entire story of the universe in a very different way. To understand why this discovery has raised so many questions, we need to return to what science has believed for decades. For most of modern history, the universe has not been seen as a chaotic and unpredictable place. Instead, it has been understood as a system with structure, governed by rules that can be described mathematically and, more importantly, tested through observation. The foundation of this understanding begins with a simple but transformative idea. The universe has a beginning. This idea is widely known as the Big Bang, and according to this model, all space, time, matter, and energy originated from an extremely hot and dense state around 13.8 billion years ago. As the universe expanded and cooled, the most basic elements began to form, primarily hydrogen, helium, and a very small amount of lithium. There was no oxygen, no carbon, and no heavy elements in this early stage. From that starting point, cosmologists built a detailed picture of how the universe evolved over time. This picture is not based on theory alone, but is supported by decades of observation from both ground-based and space telescopes. At the center of this framework is a model known as the Lambda CDM model, which is considered the standard model of modern cosmology. According to this model, the universe is not made up only of what we can see. In fact, ordinary matter, the atoms that form stars, planets, and even our own bodies, accounts for only about 5% of the universe. Around 27% is believed to be dark matter, a form of matter that does not emit light and can only be inferred through its gravitational effects. The largest portion, about 68%, is dark energy, a mysterious form of energy responsible for the accelerating expansion of the universe. Although these two dominant components have never been directly observed, the equations that describe them have proven remarkably effective. When scientists use this model to simulate the universe, the results match what is observed on large scales: the distribution of galaxies, the rate of cosmic expansion, and even the subtle fluctuations in the cosmic microwave background, the faint radiation left over from the early universe. But perhaps more important than anything else is how this model describes the formation of structure in the universe. In the traditional view, galaxies do not form suddenly. Instead, everything unfolds through a gradual and orderly process. After sufficient expansion, regions with slightly higher matter density begin to attract more material through gravity. These regions slowly grow into larger clouds of gas, and within those clouds, the first stars begin to form. These early stars are not like the stars we see today. They are known as population 3 stars and are believed to have been extremely massive, extremely hot, and very short-lived. When these stars reached the end of their lives, they exploded as supernovae, releasing the heavy elements they had created in their cores into the surrounding space. It is through these explosions that elements such as carbon, oxygen, nitrogen, and iron began to appear. These elements were then recycled to form the next generation of stars, richer in metals and more complex. This process repeated over many generations, gradually increasing the chemical complexity of the universe. This means the appearance of heavy elements is not something that can happen immediately. It requires time. Not just millions of years, but hundreds of millions, even billions of years. Stellar evolution models have calculated in detail how long it takes to produce a detectable amount of oxygen in a galaxy, and that number typically falls at no less than around 1 billion years. Alongside the formation of elements is the formation of structure. Galaxies do not appear fully formed from the beginning. At first, they exist as small, faint, and chaotic clumps of matter. Over time, these clumps collide and merge, forming larger and more structured systems. This process is known as hierarchical structure formation, where small things form first and larger structures are built gradually from them. A simple way to imagine this is to think of building a city. You cannot have a skyline filled with skyscrapers overnight. You begin with foundations, then smaller buildings, and only later do larger, more complex structures emerge. According to the Standard Model, the universe works in much the same way, and for many years, all observations supported this view. When the Hubble Space Telescope looked deeper into the universe, it revealed something very clear. The farther we look, which means the further back in time we see, the smaller, dimmer, and less developed galaxies become. This is exactly what the model predicts. There was no indication that the universe had ever behaved differently. This consistency created a high level of confidence within the scientific community. Not blind confidence, but confidence built through repeated testing, where predictions continued to match new data. For a long time, many cosmologists believed they had understood the fundamental principles governing the formation and evolution of the universe. That does not mean every question had been answered, but the remaining questions were considered refinements, small adjustments within an already complete picture. Like finishing the details of a structure whose framework is already in place, the work that remained was seen as improvement, not revision. Because of this, when the first data from a new telescope began to appear, no one truly expected it to challenge the foundation of that entire picture. What they expected was greater precision, clearer details, and perhaps a few minor adjustments. No one expected that they might have to reconsider the most basic assumptions about how the universe works. But as we have already seen, what the James Webb Space Telescope revealed does not seem to be just another detail. It is a deviation, something that does not quite fit into the picture we have drawn. And when a detail does not fit within a system that has otherwise been remarkably consistent, the question is no longer whether that detail is wrong. It becomes whether the overall picture is missing something. To understand why these recent discoveries carry so much weight, we need to look at the instrument that made them possible. On the morning of December 25, 2021, while much of the world was in the quiet stillness of the holiday, a rocket lifted off from the northeastern coast of French Guiana. Inside its payload fairing was not just a scientific instrument, but the result of more than 3 decades of research, design, and testing. The total cost of the project reached approximately $10 billion, and throughout its development, it endured multiple delays, design changes, and moments when cancellation seemed like a reasonable option. The rocket was Ariane 5, and its payload was the James Webb Space Telescope. Unlike many launch events in the history of space exploration, this moment was not followed by immediate celebration. Those who had been closely involved with the project understood that leaving the launch pad was only the first step, and perhaps the simplest part of the entire mission. The real challenge lay in what would happen next, as the telescope began its journey away from Earth. Its destination was not a low Earth orbit, where astronauts could potentially service it, but a point approximately 1.5 million kilometers away, known as the Lagrange point L2. At this location, the gravitational forces of the Earth and the Sun balance in a way that allows the telescope to maintain a stable position in deep space. But this distance also implies something very clear. If anything goes wrong, there will be no opportunity for repair. What makes James Webb remarkable is not only where it is positioned, but how it is designed to observe the universe. Unlike previous telescopes, such as the Hubble Space Telescope, which primarily operates in visible light, James Webb is optimized to detect infrared radiation. The reason for this is directly related to the expansion of the universe. As light travels through expanding space, its wavelength is stretched, shifting it from the visible spectrum into the infrared range. This means that the oldest signals, emitted by the earliest galaxies, can no longer be seen with traditional optical instruments. If we want to look further back in time, we need a telescope capable of seeing infrared light. That is the fundamental purpose of James Webb. To achieve this, the telescope is equipped with a primary mirror measuring 6.5 meters in diameter, significantly larger than any previous space telescope. This mirror is not a single solid piece, but is composed of 18 hexagonal segments, each made from beryllium, a material that is both lightweight and stable at extremely low temperatures. Each segment is coated with a thin layer of gold, not for appearance, but because gold is highly effective at reflecting infrared light. However, a mirror of that size cannot be launched in one piece. Engineers designed it to fold, allowing it to fit within the rocket and then deploy once in space. After separation from the launch vehicle, the telescope had to unfold itself through a sequence of complex mechanical movements. Each step in this sequence represented a potential point of failure, where even a small malfunction could have compromised the entire mission. Beyond the mirror, James Webb also requires an extremely cold operating environment to detect the faint signals coming from distant regions of the universe. Any source of heat, including the telescope itself, could interfere with its measurements. To address this, the telescope is equipped with a massive sun shield consisting of 5 layers of specialized material, roughly the size of a tennis court. This shield blocks nearly all thermal radiation from the sun, Earth, and Moon, allowing the instruments to remain at temperatures close to absolute zero. The temperature difference between the sun-facing side and the shaded side of the shield can reach hundreds of degrees, creating an environment cold enough for the infrared sensors to function at maximum sensitivity. All of these elements, from the mirror design to the deployment system and the sun shield, serve a single purpose: to collect the oldest light we can possibly observe. After completing its nearly 1-month journey and successfully deploying its complex systems, James Webb entered the alignment phase. The 18 mirror segments, initially operating independently, had to be adjusted with extreme precision to function as a single reflective surface. This process took several weeks, with incremental adjustments made until the individual images converged into a single, sharp point. Once this alignment was complete, the telescope was finally ready to observe. In July 2022, the first scientific images were released. They showed a tiny patch of the sky, yet contained thousands of galaxies. Each point of light in these images was not a star, but an entire system composed of hundreds of billions of stars. These images were not only visually striking, but also carried a clear implication. We were now looking deeper into the universe than ever before. At the time, most of the scientific community received these results with excitement. What they saw appeared to match expectations: more galaxies, clearer details, and greater distances than previously observed. But for some researchers, the initial reaction was not entirely enthusiasm. Because as they began to analyze the data more closely, small details started to emerge. These details were not immediately obvious. They were not groundbreaking discoveries announced right away. Instead, they appeared as minor discrepancies, numbers that did not quite align with predictions, and characteristics that did not fully match the established models. At first, these discrepancies could be explained using familiar factors, such as dust within galaxies affecting the observed color of light, or additional energy sources making galaxies appear brighter than they actually are. These explanations were tested, and in some cases, they were sufficient to account for the anomalies. But not all of them. And as more data continued to accumulate, the discrepancies did not disappear. They began to build. And it is at this point that the story begins to change. What initially appeared as small irregularities gradually turned into larger questions. No longer questions about whether the data was accurate, but about whether the assumptions underlying our models were still valid. And that leads us to the next stage of the story, where these observations are no longer isolated anomalies, but begin to form a pattern of their own. As data from the James Webb Space Telescope began to be analyzed more systematically, scientists were no longer just looking for clearer or more distant images. They began measuring specific physical properties of the galaxies appearing in these deep observations. One of the most important parameters in these studies is redshift, a way of indirectly measuring distance and time in the universe. The higher a galaxy's redshift, the more its light has been stretched, and the earlier in cosmic history we are observing it. In previous years, telescopes such as Hubble had already identified galaxies with very high redshift, but James Webb quickly pushed this limit further. Early observations revealed galaxies with redshifts exceeding 10, corresponding to a time when the universe was only a few 100 million years old. On the surface, this was not unexpected. In fact, it was precisely what James Webb was designed to do, to find the earliest galaxies. But as researchers began to examine the data more closely, they realized that these galaxies did not match what the standard model had predicted. According to earlier models, galaxies appearing at such early stages of the universe should share certain characteristics. They should be small, faint, and structurally simple, because they would not have had enough time to accumulate mass or form multiple generations of stars. In other words, they were expected to be very young systems, still in the early stages of formation. But what James Webb observed did not fully align with that picture. Some of the galaxies appearing in the data were significantly brighter than expected. This brightness was not simply a matter of containing more stars, but suggested that the rate of star formation within them could be much higher than models allowed for such a short time span. In addition, the estimated sizes of some of these galaxies were larger than predicted. Rather than being small and irregular structures, they appeared to have reached a level of development that, according to theory, should require more time to achieve. At first, these observations were approached with caution. Scientists understood that interpreting data from such extreme distances always involves uncertainties. Factors such as cosmic dust, gravitational lensing, or powerful energy sources like supermassive black holes could make a galaxy appear brighter or larger than it actually is. So, multiple research groups began testing these possibilities. They examined whether the light might have been amplified by intervening structures between the galaxy and Earth. They analyzed spectral data to look for signatures of active black holes at the center. They also revisited assumptions within the models to determine whether adjustments could be made without fundamentally altering the theory. In some cases, these explanations helped reduce the level of discrepancy. But in many cases, they were not enough. And it is here that a more specific problem began to emerge. It was no longer just a question of size or brightness. It was a question of chemical composition. When light from a galaxy is split into its spectrum, scientists can identify the presence of different elements through characteristic spectral lines. This method has been used for decades and is considered a reliable tool for studying the universe. In some of the high redshift galaxies observed by James Webb, spectral signatures indicated the presence of heavy elements, including oxygen. And according to current models, this is a problem. Because as discussed earlier, heavy elements did not exist immediately after the Big Bang. They must be produced through nuclear fusion inside stars, and then dispersed into the surrounding environment when those stars reach the end of their lives. This process does not happen instantly. It requires at least one generation of stars to form, evolve, and die, followed by the recycling of material to form a second generation. Only after multiple cycles does the abundance of heavy elements become significant enough to be clearly detectable. This sets a relatively clear timescale. The appearance of a substantial amount of oxygen in a galaxy typically requires at least around 1 billion years. But the galaxies observed by James Webb exist at a time when the universe was only about 200 to 300 million years old. This difference is not a small discrepancy. It is a large gap. And if the measurements are correct, it means that the processes of star formation and element production must have occurred much faster than we previously thought. Another way to understand this is by considering how quickly a galaxy can mature. In standard models, the development of a galaxy is a gradual process. It begins with small clouds of gas, which slowly accumulate more material, form stars, and develop structure over hundreds of millions of years. Reaching a stable state with multiple generations of stars and complex chemical composition is the result of a long history. But the galaxies observed by James Webb appear to have bypassed part of this process. They show up in the data with characteristics of already developed systems, even though, according to the timeline of the universe, they should not have had enough time to reach that state. To visualize this, imagine a group of newborns, but among them is someone fully grown, not just slightly more developed, but in a completely different stage compared to what would be expected. This is not only surprising, it raises a fundamental question. Are our models underestimating the speed of these processes, or is there something about the early universe that we do not yet fully understand? In the early stages of interpretation, some researchers considered the possibility that these galaxies might have experienced extremely intense periods of star formation, known as starbursts, where the rate of star formation increases dramatically over a short period of time. In theory, such events could produce large numbers of stars and heavy elements more quickly than usual. However, even with this assumption, the numbers do not fully match. To reach the observed levels of oxygen, these galaxies would likely require not just a single starburst event, but multiple cycles of star formation occurring in rapid succession. This would imply that the initial conditions of the universe were significantly different from what current models describe. And this is the point where the story begins to shift from isolated anomalies to a systemic issue. No longer just one galaxy or a few exceptional cases, but a trend, a new pattern beginning to emerge from the data. And when a new pattern appears, it does not only question small details, it begins to challenge the most fundamental assumptions. This does not necessarily mean that the entire existing theory is wrong, but it suggests that we may be missing a part of the story, a part significant enough to change how we understand the entire process of cosmic structure formation. And as more observations are made, these signals do not disappear, they become clearer. And this is the point when scientists begin to ask whether this is just a temporary anomaly or the first sign of something much larger waiting to be understood. If the observations from the early stage had remained limited to just a few isolated cases, the story might have ended there, with localized explanations and minor adjustments to the model. But as data from the James Webb Space Telescope continued to expand, something began to become clear. These anomalous galaxies were not exceptions. They were appearing more frequently than predicted. At first, scientists approached each object individually, examining specific cases to find reasonable explanations. But as the number of galaxies with similar characteristics began to increase, it became harder to treat them as independent anomalies. Instead, they started to form a group and then a trend. Several deep surveys from James Webb have reported a significantly higher number of bright, well-developed galaxies in the early universe than predicted by simulations. This discrepancy is not just a matter of a few percent. In some cases, it is several times higher. This suggests that it is not simply a few galaxies forming faster than expected, but that the entire process of structure formation in the early universe may have unfolded differently. The problem is no longer about explaining a single data point, it is about explaining a distribution. When a model is built, it does not only predict the existence of a specific object, but also the frequency and distribution of such objects across the universe. If the observed numbers deviate significantly from predictions, the question is no longer, why is this object unusual, but why is the model wrong on a large scale? This marks a critical shift in perspective, from a single anomaly to a pattern. And when a pattern begins to emerge, the seriousness of the problem changes. Alongside the growing number of anomalous galaxies, another issue, one that had already existed before, began to gain more attention when placed in the same context. This is the problem of cosmic reionization. After the Big Bang, the universe entered a phase in which electrons and protons combined to form neutral atoms. This made the universe effectively opaque to certain types of radiation, because light could be easily absorbed by these neutral atoms. Only when powerful sources of energy, such as the first stars or early galaxies, began emitting sufficient radiation that these atoms become ionized again, allowing light to travel more freely. According to current models, this process of reionization occurred gradually over an extended period and was not completed until the universe had reached a certain age. This implies that if we observe galaxies at very early times, their light, especially at specific wavelengths, such as Lyman alpha, should be significantly absorbed by the surrounding medium. But in some observations from James Webb, that light is still visible. This is not a minor detail. It suggests that the environment around these galaxies may have been ionized earlier than predicted, or at least in localized regions where these galaxies exist. And this leads back to the original issue. To ionize the surrounding medium that early, there must have been strong sources of energy operating at very early times, meaning more stars, more galaxies, and more intense activity within a shorter period. These two problems, when considered together, begin to reinforce each other. On one side, we have more galaxies forming and evolving faster. On the other, we have an environment that appears to have changed state earlier than expected, and both point toward the same conclusion. The early universe may have been more dynamic and more complex than we have described. But perhaps the clearest point of tension between theory and observation does not come from those distant galaxies. It comes from how we measure the expansion of the universe itself. For many years, cosmologists have relied on a key parameter known as the Hubble constant to describe the rate at which galaxies move away from each other. This is not just a number, but a fundamental part of how we understand the history and future of the universe. There are multiple ways to measure it. One method relies on observations within the nearby universe, using objects such as variable stars and supernovae to estimate distances directly. This method tends to produce a higher value. Another method relies on analyzing the cosmic microwave background, the faint radiation left over from the early universe, and using models to infer the present expansion rate. This method tends to produce a lower value. For a long time, the difference between these results was treated as a technical issue, something that could be resolved with more precise measurements. But as precision improved, the difference did not disappear. It remained, and in fact, it became more pronounced. This creates a situation where two independent methods, based on entirely different types of data, both produce consistent results within their own frameworks, but are inconsistent with each other. This is not a random error. It is a systematic tension. And when the data from James Webb is added to this picture, the question is no longer just about measurement. It becomes a question about the model itself. If the same model is used to interpret both types of data, but leads to different conclusions, then the issue may not lie in the data. It may lie in the model. When these three elements are considered together, the abundance of anomalous galaxies, the signs of early reionization, and the tension in the Hubble constant, they begin to form a larger picture. No longer separate problems, but pieces that do not quite fit together. At a surface level, each issue may have its own explanation, but when viewed as a whole, relying on separate explanations for each becomes less convincing. This leads to a simple but uncomfortable realization. It may be that the framework we are using to describe the universe does not fully reflect reality. Or in other words, the map we have drawn does not perfectly match the territory it represents. This does not mean that modern cosmology is entirely wrong. Most of what we know still works well in many situations. The equations continue to describe many phenomena accurately, and predictions are still confirmed in numerous contexts. But what is emerging suggests that there may still be important elements missing from the model, elements that do not necessarily invalidate what we already know, but may change how we understand the formation and evolution of the universe. And as more data continues to be collected from deeper observations, these signals do not fade. They become more consistent, more defined, and harder to ignore. This is the point where the story moves into a different phase. No longer about identifying whether anomalies exist, but about understanding what those anomalies are trying to tell us. When these anomalies can no longer be treated as isolated cases, the next question is no longer whether they exist, but how we explain them. In science, when data begins to diverge from a model, the first response is rarely to replace the entire theoretical framework. Instead, researchers try to adjust uncertain components, introduce new factors, or revisit assumptions that were previously considered reasonable. This leads to the emergence of multiple hypotheses, not as complete answers, but as possible directions that might help narrow the gap between theory and observation. One such direction considers the possibility that dark energy, the dominant component of the universe in the Standard Model, may not be constant over time. In the current model, dark energy is typically treated as a constant, meaning its density does not change as the universe expands. But if this assumption is not entirely accurate, then the way the universe expanded in its earliest stages may have been different. The idea of early dark energy arises from this context. According to this hypothesis, dark energy may have played a stronger role in the early universe than it does today, and then gradually decreased over time. If this is correct, the early expansion rate of the universe could have been higher, allowing structures to form more quickly within a shorter period. In theory, this could help explain why we observe galaxies that appear more developed than expected. However, introducing such a component into the model is not a simple solution. Any change in the expansion history of the universe affects multiple observations, including the cosmic microwave background and the large-scale distribution of galaxies. A new model must not only explain one discrepancy, but remain consistent with everything that has already been confirmed. And so far, no version of this hypothesis has achieved that in a fully convincing way. Another approach does not focus on changing the contents of the universe, but rather the way gravity itself behaves. For over a century, general relativity has provided the foundation for understanding gravity on large scales. Its equations have been tested in many different contexts, from planetary motion to the bending of light around massive objects. But when applied to the universe on the largest scales, or under extreme conditions, some researchers have begun to question whether the theory might need to be extended or modified. This is where the idea of modified gravity emerges. If gravity behaves differently or more strongly under the conditions of the early universe, then matter could have collapsed more quickly, forming larger structures in less time. This could potentially explain the presence of mature galaxies at very early epochs. However, as with dark energy, modifying gravity is not something that can be done without consequences. Observations of galaxy motion, the formation of galaxy clusters, and even precise measurements within our own solar system impose strict constraints on any alternative theory of gravity. A small change in the equations can lead to significant consequences across many areas of physics. This means that any alternative gravitational model must pass a wide range of rigorous tests. And so far, none have been able to fully replace the existing theory without introducing new issues. Another hypothesis, less intuitive but still considered in this context, involves the possibility that certain structures may have existed from the very earliest moments of the universe. In the Standard Model, black holes are typically formed from the collapse of massive stars at the end of their life cycles. But there is another possibility, that some black holes could have formed directly from density fluctuations in the early universe before the first stars ever existed. These objects are known as primordial black holes. If such black holes exist in sufficient numbers, they could act as strong gravitational seeds, accelerating the accumulation of matter and triggering faster galaxy formation. This could lead to large and complex structures forming much earlier than predicted by standard models. However, evidence for primordial black holes remains limited. At present, they exist mostly as a theoretical possibility, supported by some indirect hints, but not yet confirmed. And like the other hypotheses, incorporating them into the model introduces additional consequences that must be tested in multiple contexts. What all of these approaches have in common is that they attempt to resolve specific problems by extending or modifying the current model. But when viewed as a whole, none of these hypotheses fully explains all of the observed anomalies without introducing new questions. This leads to a simple but difficult realization. We may not yet have enough information to provide a complete answer. Or more directly, we do not know. In science, Not knowing is not a failure. In many ways, it is the starting point for discovery. But it also reflects a reality. The models we use, no matter how powerful, are approximations of the real universe. They work well in many situations, but not necessarily in all. And when new data begins to emerge, especially from regions we have never observed before, the limitations of those models begin to reveal themselves. On a human level, this also creates a very specific response. Not panic, but hesitation. Some scientists begin to re-examine assumptions they have relied on for years. Equations that once seemed foundational are now placed in a new context, where they may need to be extended or refined. Some describe this process as learning to see the universe again, not from the beginning, but from a different perspective. And in some cases, that is not easy. There are nights when the data does not align with the model and no clear explanation is available, when the question does not stay confined to the page. It remains even after the work of the day has ended, not because it is urgent, but because it is unresolved. This brings us to a point where science is no longer a collection of definitive answers, but an ongoing process of questioning and reevaluating what we think we understand. Hypotheses are not proposed to declare truth, but to test whether they can bring the picture into better alignment. And at this moment, that picture is still incomplete. This does not diminish the value of what we already know, but it reminds us that our understanding of the universe is always provisional. And sometimes, what appears to be a small detail may be the first sign of something much larger waiting to be discovered. As we step back and look at this entire journey, from the initial assumptions to the anomalies that have gradually become clearer, one thing begins to stand out. The story is not over. The James Webb Space Telescope is not a completed experiment, nor is it a fixed source of data that has already been fully explored. It is still operating, still collecting signals from regions that are farther, deeper, and older in the universe. With each passing day, it continues to send back new data. And within each new data set, there is always the possibility that a single detail could reshape how we understand the entire picture. This means that what we are seeing now is not a final answer. It is only part of a much longer process, a process in which each new observation does not simply add information, but sometimes introduces entirely new questions. If there is one thing these recent discoveries remind us of, it is that the universe may be far more complex than we have described, not because previous models are entirely wrong, but because they may not capture every aspect of reality. For many years, the scientific approach has been to build increasingly precise models, supported by increasingly detailed data. And in most cases, this approach has worked remarkably well. But as we begin to observe regions that were once beyond our reach, the limitations of those models begin to emerge. This is not a failure. It is a natural part of how science works. Science is not a static system. It is not built to preserve a fixed set of answers, but to continuously adapt and expand as new data becomes available. What is considered certain at one moment may become the starting point for new questions at another. And in that context, uncertainty is not something to avoid. It is part of the process of understanding. When scientists encounter data that does not align with existing models, they do not immediately discard what they know. They re-examine it, they compare, they test different hypotheses, and sometimes they must accept that certain things cannot yet be explained. This does not diminish the value of science. On the contrary, it shows that the process is still ongoing. In the case of the distant galaxies observed by James Webb, this means we are facing a set of data that does not yet have a complete explanation. It is possible that future observations will clarify what is happening. It is possible that some anomalies will be explained by factors we have not yet considered. And it is also possible that parts of our current models will need to be revised. But at this moment, the most important thing is not to reach a final conclusion. It is to recognize that the question remains open. In some sense, this also changes how we see our own place in the universe. When we observe galaxies billions of light years away, we are not just looking at distant objects. We are looking into the past. The light we receive today left its source long before Earth formed, before the sun existed, and even before the earliest structures of the universe were complete. This means that every observation is a glimpse into the history of the universe itself. And in a way, it is also a glimpse into our own history, because the elements that make up our bodies, carbon, oxygen, iron, did not exist at the beginning. They were formed inside stars through processes that lasted millions of years and were released into space through stellar explosions. From there, they became part of new star systems, new planets, and eventually, life. This creates a direct connection between astronomical observation and our own existence. When we look at the earliest galaxies, we are witnessing the first steps of a process whose final result is our presence here. And if these observations suggest that this process may have unfolded differently than we once believed, then this is not just a technical detail. It is a reminder that our understanding always has limits. This does not make the universe more confusing in a negative sense. Instead, it makes it more meaningful, because every new question opens the possibility for discovery, and every adjustment to our models brings us closer to a deeper understanding, even if we may never reach a complete answer. In that context, perhaps the most important thing is not whether we can explain everything immediately, but that we continue to observe, to continue asking questions, and to accept that part of this journey is learning to live with uncertainty. And if you have followed this story this far, through the quiet of space and time, you can like the video or subscribe to the channel. It is a small action, but it helps content like this reach more people, those who are searching for questions rather than simple answers. When we look out into the universe, we are not just observing distant points of light. We are observing a process that has unfolded over billions of years, where matter, energy, and time interact in ways we are only beginning to understand. And in that process, we are also trying to understand ourselves, because at a very fundamental level, we are looking into the past and seeing the origins of who we are. And perhaps what this story is truly about is not a distant galaxy, but the feeling that we may not yet understand the universe in the way we think we do.